Artificial structures on the St. Petersburg flood barrier. On the 12th of August 2011, the St. Petersburg flood barrier causeway was opened to traffic. The event marked the completion of the ring road, as well as of construction of the flood barrier itself. The main purpose of the barrier is to protect St. Petersburg and its surroundings from flooding. The barrier is designed to protect against a rise in water level of up to 4.55 meters, a level of flooding that occurs once every 1,000 years. The barrier includes 6 sluice gates, named B1 to B6, which allow water from the Neva River to flow into the Gulf of Finland. There are also 2 additional locks, named C1 and C2, which allow water as well as ships to pass through. The width of the water reaches a total length of 1,536 meters, with a depth of 2.5 to 5 meters. It is 50% longer than the Neva River estuary is wide. Stretching for 25 kilometers along the Neva Bay, the embankment dam joins the village of Gorskaya to Kronstadt on Kotlin Island and onward to Bronka station in Lomonosov. Additional structures have been designed and built in order to allow vehicles to pass through the dam's barriers. For design and exploration work, the client turned to the experienced team at Len Transmost, now known as Transmost plc. The following structures were built according to Transmost project documentation. The underwater tunnel in structure C1. The vertical lift bridge in structure C2, superstructures for sluice gates B1 to B6, viaduct to Bronka railway station, 2 temporary bridges on fill dams D2 and D7, which allowed water to flow through the dam even when the sluice gates and navigation channels were under construction. In order to allow motor vehicles to travel in the vicinity of navigation tunnel C1, an underwater tunnel under the Gulf of Finland was constructed. The tunnel runs for a total of 1,961 meters, with an underground segment of 1,189 meters and 2 ramps of 386 meters each. The tunnel's foundation pit is 28 meters below the level of water in the Gulf. The underground segment is divided into 60-meter sections. Viewed in cross-section, the underwater tunnel segment appears as a 5-span reinforced concrete frame 42 meters wide and 10 meters high. The tunnel is wide enough for 6 lanes of traffic, with 2 compartments holding 3 lanes each, separated by a servicing and evacuation compartment in the middle. The transport compartment is 15.25 meters wide. Auxiliary cabling is threaded through 2 dedicated compartments. The tunnel is also fitted with ventilation, lighting, internal fire extinguishing equipment in the transport and servicing compartments, video surveillance, automation, an alarm system, communications, an evacuation system, automated management of routine processes, and a dispatch center. As part of the structure C2, motor vehicles pass over the vertical lift bridge, which allows ships through the northern shipping channel. The channel is made for relatively small ships that operate regionally. The bridge itself is 1,078.65 meters long, while the full crossing spans 1,483 meters. As designed, the crossing has the dimensions 10 by 27.0 plus 6 by 33.0 plus 120 plus 6 by 33.0 plus 10 by 27.0 meters, with an adjustable span vertical lift system over the riverbed part. The width of the roadway part measures 13.25 plus 0.8 plus 13.25 meters. It is designed to fit 6 lanes of traffic, moving at speeds of up to 120 kilometers per hour. While outside guide towers are usually used to house hoists for raising and lowering bridge spans, the 120-metre steel span for St. Petersburg's barrier has no need for such towers. When lowered, the bridge accommodates ships of up to 16 metres tall. Ships of up to 25 metres in height can pass through when it is raised. 4 steel support frames lift up the span. Each frame consists of 2 front box cross-section posts located inside the bridge supports. Cables for the raising mechanism are wrapped around the lower crossbeams. The vertical structure weighs 2,300 tonnes, with counterweights of 1,140 tonnes each to balance it. The span was lifted to the necessary height by a cable system that Swiss firm VSL helped to develop. Bridge raising and lowering, as well as traffic barrier and navigation warnings, are managed from control boards. From the very beginning of the dam project, minimizing the potential harm to the Gulf of Finland was a priority. 6 sluices were constructed to this end. The sluices permit water to flow between the Gulf of Finland and the Neva Bay. For the vehicle bridges over sluices B1 to B6, Transmost joined with the Moscow State University of Railway Engineering to make original designs for precast concrete spans, consisting of reinforced concrete beams of 27 and 26 metres. For the first time in Russia, the bridge builders used optimal compression beams, made from pre-stressed concrete. These designs reduced concrete use by 15 to 18% and reduced the mass of the installation constructions. The viaduct at Bronka station, which crosses the railway and the Krasnoflotnaya highway, is one part of the transport hub on the south shore of the Gulf of Finland. The viaduct dates to the mid-1980s and is built of precast reinforced concrete with pillars on pile foundations. Thanks to the resilience and ingenuity of engineers, builders, planners, local government and federal authorities, this huge structure has been completed, bringing great social and economic benefits.